First, I would like to give you a brief outline what I will talk about. I will start with presenting you two obstacles of scaling up reinforcement learning. Then I will go to obstacle one, which I will reveal in a moment. And then I will tell you about our work, which is JaxGCRL goal-conditioned reinforcement learning, our framework. And at the end, I will tell you about obstacle number 2 and our results. But before going to these obstacles, let's have a moment and think of the dream of reinforcement learning. How autonomous agents would work alike if everything would be perfect. So, for sure, they will learn new emergent behaviors the longer they are trained. So they will start with simple unstructured interaction with the environment, but then they will develop more and more complex behaviors. And what is also important, there will be no human supervision involved in the process. So we would like to have agents that we don't need to reward, to shape the reward for. But even though this vision is quite feasible, we have still two obstacles to bypass. The first obstacle is that we need a massive amounts of data. Currently, we are using relatively small data sets. They are of order of maybe 1 million transitions for very popular benchmarks like DeepMind control suite. But what will happen if we scale those millions of transitions to billions of transitions? Will we observe some emergent behaviors as we observe in natural language processing? And the second obstacle is that we need algorithms and architectures that can really utilize this data. Because data only is not enough, so we need expressive architectures. But let's start with the first obstacle, because it's easier. We have seen in other domains that just pouring more data to the model just works. So if it works also in reinforcement learning, let's see. But why we are having problem with data? It is because for a long time we were doing something super unoptimal. We were running reinforcement learning methods on two devices. One device is a GPU on which the whole learning of the agent is done. And the second device is CPU on which we are generating data. So it is not the perfect solution because we have a lot of time waste on transferring the data between these two devices. And what's more, we are also not utilizing GPU as we should. And to run really high scale, big scale experiments, we would need number of servers to gather enough data to really do big training. So to give you some example, training reinforcement learning, for example, soft actor critic architecture on DeepMind control suite took around 4 to 8 hours per experiment to finish. But right now, there is a trend of using JAX accelerated environments. So these environments are run on GPU devices. And what is really important, that right now we can compile a whole training loop into a single program that is running pretty fast. And what's also very important is that we can run thousands of environments on a single GPU. So we are also in this trend, and we in our recent work, JaxGCRL, we released a new benchmark and codebase for fast experiments in reinforcement learning. And you can find in our package more than 10 GPU-accelerated environments, which are extremely fast. Because right now you can run experiments that previously took hours, and now you can run them in 10 minutes. And what is also important, it's easy to modify and extend, and it is shown by traction that is that we are getting recently from the contributors. And another important thing is that it is based on open source codes. So it's based on Brax and MJX, which are physics simulators that are currently under development and are pretty fast. So to give you main results from our work, we re-implemented a contrastive reinforcement learning method that I will talk to you about in a moment, and compared the training speed up on our implementation and the previous implementation. As you can see in the plot, there is almost 20 times faster training in our repository, and it is due to using this single GPU, but on which we have all of the data, all of the training and environments. So what exactly does our repo enable? Right now, you can work on reinforcement learning projects like on data science ones. So you can pretty quickly iterate and have a quick feedback loop of what is working and what is not working. Previously, you had to wait a day for experiments to finish. Right now, you can have results in 10 minutes and implement another idea. This is a big thing. And another thing is that you can right now contribute to reinforcement learning research with just single GPU and your home PC. It won't last long, I guess, because we will see some improvement in models and model scale in a moment. But right now, it's a good moment for contributing in RL just with single GPU. Here you can see a sample of our environments in the repository. So you can find here really popular ones like Ant or Reacher, but you can also find ones that are more complex, like navigating Ant maze, or models that are based on physical robots like Franca, which are high-dimensional and pose a challenge to reinforcement learning algorithms. All right, so we know that there is a movement of bypassing the obstacle number one, which is data. But how about obstacle number two? Obstacle number two is related to how we can scale algorithms architectures to utilize this data, once again. So recently, the colleagues of mine published a great paper, which is called BRO. It was published on NeurIPS this year with Spotlight, and they were attacking this problem of scaling up reinforcement learning. They did a pretty good job, and they scaled soft actor critic to state-of-the-art performance. However, as you can see, models that are 5 million parameters big and those that are 5 times larger saturate almost on the same performance level. So it seems like there is still a problem with proper scaling of architectures in reinforcement learning. But before I will jump into other ideas for architectures, I would like to give you a short summary of how goal-conditioned reinforcement learning works so that we are all on the same page. Here you can see that reinforcement learning with a goal is that we specify some state that we want the agent to reach. In this example, we have ant that is navigating around a plane, and it needs just to reach this blue blob. So, so the policy of the agent is not only conditioned with a state, but also on the desired position in this example. And important thing is that this goal-conditioned RL often is merged with sparse reward setting. Sparse reward setting is a step towards removing human supervision in reinforcement learning by only specifying the goal and not the whole movement of reaching the goal. So in most of the reinforcement learning setups, you need a dense reward that tells you how exactly to move the agent. And here you have just a binary condition that tells you, oh, you reached the goal or you didn't. So it removes a lot of work from the programmer. But going back to architectures and different ideas of how to improve reinforcement learning, 2 years ago, Benjamin Eisenbach proposed a pretty interesting notion that breaks a bit with a tradition of reinforcement learning, because here he cast the reinforcement learning problem as a classification problem. So the idea here is that you can you should discriminate future states in the trajectory. So one robot movement, for example, or one play of the Atari game. You should discriminate future states that happen in the same trajectory from those that are happening in other. So you are basically trying to learn metric that tells you how similar are the states and how easily you can move from a particular state to another. And this is achieved by taking embeddings of state action pairs and state embedding that comes after this state action, and contrasting it with those that are from other trajectories. And we are using different energy functions that measure this similarity, and we can also use different contrastive objectives that optimize these energy functions. It works, and it works pretty well because it learns the environment dynamics. So as you can see in this example, states, we have these embeddings of the states, actions, and goal projected on a 2D plane. And as you can see, states in which robot already grasped the box are much closer to the goal embedding than those in which the robot is just moving a hand towards the box, because the task is to move the box from one bin to another. So contrastive reinforcement learning really creates this better notion of closeness, and especially in high-dimensional state spaces. But how does it relate to our work? Well, we re-implemented this method and two other baselines, which is soft actor critic and soft actor critic with hindsight experience replay, and run a comparison between all of these three. And what we found is that only contrastive reinforcement learning works well in all of the proposed environments from our benchmark. We then asked a question that right now it's pretty easy to scale the data. So we can already go from millions of environment steps to hundreds of millions of environment steps. And we wanted to see whether out of the box we have some scaling properties of this algorithm. However, as you can see in these plots, the performance in most of the environments saturates pretty quickly, and it saturates not on very high performance. So it seems like that even for these different combinations of energy functions and contrastive objectives, there is some other factor that is a bottleneck in this scaling. So we dive deeper into what exactly contrastive objectives and energy functions combinations work. And what we find out that in general, there are some that doesn't work at all and are pretty bad, but also there are some that if they work pretty much the same. So it also pointed us to the direction that perhaps there is something else which is a bottleneck right now. And the bottleneck seems to be the architecture scale. So we were improving and scaling up architecture of contrastive RL agent. And as you can see, the performance were increasing with a higher number of parameters and bigger depth of the agent. However, for 1,000 hidden neurons, we see that this scaling saturates. So we use some tricks from that are pretty popular in natural language processing, but only right now are getting more popular and getting traction in reinforcement learning, which is layer normalization. And it turned out that it helps us with scaling the performance even further. However, it is still an ongoing project, so we are still super interested in how to improve expressivity of these contrastive architectures. But this is for future talk. So the main takeaways from today's talk are that there are two obstacles right now. And the first obstacle, the data, is pretty much mitigated by all of these parallel environments in JAX. However, the second obstacle, I guess, is more burning. With our work, JAX goal-conditioned RL, we effectively improve the obstacle one, and especially in the niche of goal-conditioned RL, and we are speeding up the research on the obstacle two, because right now we can done experiments that previously took days in a few hours or even minutes. So citing Jacob Forrester, it seems like there is another seismic shift in this field, and it's a pretty interesting moment to be in RL because you can contribute without much of resources. So this is all for today. Thank you very much, and I'm happy to answer your questions.